Sometimes the rate of a reaction is affected by the concentration of one or more of the reactants, and sometimes it isn't. We express the dependence of the rate on concentration of the reactants according to an expression called the rate law. The rate law is an equation that relates the concentration of reactants to the rate, assuming that the reverse reaction is negligible. The rate law expresses the rate of a reaction as directly proportional to the concentration of each reactant raised to a power times a K that's specific for that reaction. So the K is just a constant called the rate constant that's specific for that particular reaction. Here we see a rate equation for the reaction where A is forming products. The rate is equal to some K times the concentration of A raised to the n power. N, called the order, is an integer that determines the rate's dependence on that reactant's concentration. The exponent on each reactant in the rate law is called the order with respect to that reactant, and the sum of the exponents on the reactants is called the overall order for the reaction. For example, in the rate law, where the rate is equal to K times the concentration of NO squared times the concentration of O2 to the first power, the reaction is second order with respect to NO, and first order with respect to O2, and third order overall, because the sum of the exponents is 3. Let's consider a bit further how the order of a reactant affects the rate. So, for example, where the rate is equal to some K times the concentration of A raised to the n power, if the reaction is zero order with respect to that reactant, the rate of the reaction won't change even if you change the concentration of that reactant. For example, doubling A will have no effect on the reaction rate. If the reaction is first order with respect to that reactant, the rate is directly proportional to the reactant concentration. So doubling A doubles the rate of the reaction. If a reaction is second order, the rate is directly proportional to the square of the reactant concentration. So doubling A will quadruple the rate of the reaction.